First and foremost, when you think of amines, you should think of them as bases. Just like when we dissolve a carboxylic acid in water, the solution is acidic. When you dissolve an amine in water, the solution is basic. Just how basic amines are can be illustrated by two equations. First, recall that alcohols act as bases. An acid as strong as sulfuric acid is used, and under those conditions, the alcohol is significantly protonated to shift the equilibrium to the right. In contrast to protonate an amine, all we need to do is put it in water. As you know, water is not real acidic, and yet when an alkyl amine is put in water, it's nearly fully protonated. What's the explanation for the different basicity of these two compounds? Well, it's the availability of the pair of electrons on oxygen or nitrogen for sharing to make a bond with a proton. This pair of electrons on oxygen is held rather tightly because oxygen is pretty electronegative. On the other hand, this pair of electrons on nitrogen is held much less tightly because nitrogen has nowhere near the same electronegativity. That's the difference. So we can say that basicity, the strength of a compound as a base, is determined by the availability of the unshared electron pair to form a bond with a proton. And I've highlighted proton for a good reason. Nitrogen also can use that electron pair to form a bond with carbon, and the ability to act as a base or a nucleophile isn't exactly in the same order. It's nice to know that we can say amines are much more basic than alcohols, but it would be really good to put amines on a scale that really rates the basicity so we can compare those basicities much more carefully. We need a scale that rates basicities. Well, let's take a look at the scale we use to rate acidities and then go from there. We use pH as our acidity scale, and this is a pretty odd scale. The numbers go from 0 to 14, and the small values are the strong ones. So the range is roughly from 0. There actually are negative numbers as well. From 0, we can say strong acid, and the value of 7, right halfway between 0 and 14, is what we call neutral. The solutions are neither acidic nor basic. And when we get all the way to the scale of pH equals 14, we have a strong base. So values in this region we call acidic, and values in this region we call basic. And this whole numerical scale is used, so we can pinpoint relative acidity or basicity of these solutions. What these values are telling us is the concentration of H3O+, the hydronium ion, in the solution. And for pH 0, the concentration is 1. For 7, the concentration is 10 to the minus 7th. This is a very small number, and there's virtually no H3O+ in solutions that have a pH of 14. This is 10 to the minus 14th, an unimaginably small number. So this scale lets us pinpoint relative acidities. Take a look. To illustrate the range of acidities, I'm going to use a table that has 4 different compounds in it. First, look at trichloroacetic acid. It has a pKa of 0.9, and it is a strong acid. Acetic acid isn't nearly as strong. It has a pKa of 4.7. It's still an acid, and when you put it in water, the equilibrium is shifted to the right. When we look at phenol, it has an acidic OH, but not enough so that we can simply say the equilibrium is shifted to the right in water. The pKa is 10, and it's a weak acid. It does give up a proton to water, but not completely. And finally, I put methanol on the list. Methanol is a representative of a regular alcohol. It has a pKa of 15.2, and it really is a very weak acid. When we dissolve methanol in water, there is very little methoxide and H3O+ formed. Now this pKa scale then helps us understand the relative acidities of these 4 compounds. Now remember that the pKa value is the value at which the acid is half deprotonated. So there's an equal amount of acid and its conjugate base in solution at the pH of that pKa number. So at pH 0.9, there's an equal amount of trichloroacetic acid in its carboxylate salt. Notice, too, and this is where I'm headed with all this, that when we have a strong acid, we have a weak base as the conjugate base. And when we have a weak acid, we have a strong base as the conjugate base. And we know this is true. Methoxide is a strong base. is the conjugate base of this very weak acid. The pKa value of 10 compared to 15 tells us that phenol is a stronger acid, so its conjugate base is a weaker base than methoxide. I'm just going to put base rather than strong base. And the pKa of 4.7 tells us that acetic acid is much stronger acid than phenol, so its conjugate base is a much weaker base. And finally, the conjugate base of trichloroacetic acid is even weaker. It's a very weak base. So do you see what we've done? We put the bases in order of basicity while we were writing down the pKa values of their conjugate acids. This is the system we typically use for designating the basicity of bases in organic chemistry. We talk about the pKa value of their conjugate acids. Larger value, stronger base. Smaller value, weaker base. Using this scale for basicities, larger values mean stronger bases. That's really important when we use pKa values to talk about acids. Remember that smaller values mean stronger. When we use pKa values to talk about the strength of bases, larger values mean stronger. It's just the opposite. And acids and bases are the opposite of each other, so that makes sense. So let me use this pKa scale, the pKa of the conjugate acid, to take a look at a variety of bases to see the range of basicities we could be talking about. First, let's look at ammonia. That's a standard basic substance that you saw in general chemistry. The conjugate acid is ammonium and its pKa is 9.3. The equivalent of ammonia in organic compounds would be something that has alkyl groups attached to nitrogen instead of hydrogens. So here's trimethylamine. And notice it has a very similar pKa for its conjugate acid. Let's look at methoxide. We know that's a strong base, and look at it. Its conjugate acid has a pKa of 15.2. It's a much bigger number, and methoxide is a much stronger base. On the other hand, going to weaker bases, we have some other organic structures. Pyridine has pyridinium as a conjugate acid, and its pKa is 5.1. Smaller number, weaker base. Aniline, another aromatic amine, but now the nitrogen is attached to the ring. It's not in the ring. Aniline has a pKa for the anilinium ion of 4.6. Smaller number, weaker base. And finally, look at pyrrole. Pyrrole has a pKa for the protonated form that varies depending on where you look it up. Some charts say it has a -4 value, others 0. So it's a range of 0 to -4. It's a very, very small number, and pyrrole is not a base. Aniline is a weak base, so is pyridine. Ammonia is stronger, it's a real base. And trimethylamine is similar, and methoxide is a strong base. So there's our scale, and the larger values mean stronger. A weak value, even negative, means not a base at all. And we have the whole range in between. Now here's an interesting structure, imidazole. I bring it up because imidazole is an important structural component of histidine. And histidine is one of the amino acids that makes up proteins, peptides, and in fact it's the imidazole structure that often is involved in the catalytic action of a protein to make a reaction happen by accepting a proton or donating a proton. Now we know physiological pH is about 7.3. And look at the pKa of the protonated imidazole. It's almost exactly physiological pH. Now I have a question for you. Which nitrogen is protonated when it is protonated? It turns out to be an easy one to answer. This nitrogen is like the nitrogen in pyrrole. And we know that pyrrole nitrogen isn't protonated at all. This nitrogen is like pyridine. And we know that the pyridine nitrogen is protonated. It's a weak base, but it's a base. It turns out that the structural features of imidazole that make it different from pyridine make imidazole a bit stronger base. It's just enough stronger so that at pH 7 it's half protonated. Just exactly what you'd want for a physiological catalyst. Something that will accept a proton or donate a proton easily at pH 7.3. And finally, let's take a quick look at the rationale for explaining the relative basicities. Well, looking at pyrrole, This pair of electrons is needed for the aromatic ring. If this nitrogen is protonated, that unshared pair is no longer available to participate in the aromatic pi system, and we destroy the aromaticity. You know being aromatic is much more stable, so it's way uphill energetically to protonate that nitrogen. So pyrrole is not basic. This unshared pair of electrons is in an orbital that overlaps with the aromatic ring pi system. So we can say it's conjugated with the pi system, and conjugation is good. When we protonate in that pair of electrons, that conjugation is destroyed. So that's going uphill. What about pyridine? That unshared electron pair is not needed for the aromatic ring and can't overlap with it because it's orthogonal to it. But this pair of electrons is in an sp2 orbital because nitrogen is sp2 hybridized. As a result, it's in an orbital that's closer to the nucleus. It has more s character. Nucleus has positive charge and holds the electrons tighter. The unshared pair in ammonia and trimethylamine is held by the less electronegative nitrogen, so it's not held as tightly. Look at the electrons in methoxide. They're on the more electronegative oxygen, yes, but there's a negative charge. The negative charge on methoxide makes methoxide less stable and makes the electron pair more available for protonation. So this order of basicity is readily understood simply by looking at how available that unshared electron pair of nitrogen is for bonding with a proton.